Today I'm going to be solving the CIE AS Chemistry May-June 2025 paper 32. So we're asked to read through the whole method before we start any practical work and to generate a table of results in the space provided. We are told to show precision of apparatus, so putting our answers to appropriate number of decimal places when recording our data, and to show any working out and use appropriate significant figures, usually 2 to 4, in the final answer to each step of our calculations. So it says here, acids donate hydrogen ions in aqueous solutions. They're proton donors. And the number of moles of hydrogen ions donated per mole of acid is called the proticity of the acid. So for example, sulfuric acid, which has the formula H2SO4, donates 2 moles of hydrogens per mole of acid. So as you can see in the formula, there are 2 hydrogen atoms per 1 mole of sulfuric acid. It says in this experiment we're going to calculate a titration to determine the proticity of citric acid, C6H8O7. Okay, so the method is as follows. Firstly, we need to fill a burette with FB2. Our FB2 here is our aqueous sodium hydroxide, and it is of 4.5 grams per decimeters cubed, okay? Next, we are told to pipette 25 centimeters cubed of FB1 into a conical flask. Our FB1 is our citric acid. Using a 25 centimeter cubed pipette and 7.5 grams per decimeters cubed of this. Then it says to add a few drops of FB3 into the conical flask. So using a small little dropper, add this amount of. So obviously up here would be the citric acid, down here would be, or all together really, actually, would be a mix of citric acid alongside our indicator, thymolphthalein. Or I'm just going to write down indicator. Okay, carry out as many accurate titrations as necessary. Make sure any recorded results show the precision. Record in a suitable form in the space below all your burette readings and the volumes of sodium hydroxide added in each accurate titration. Okie dokie. Okay, so I've just generated a couple of accurate results, and the first thing we're going to do is you're just going to carry out this experiment like 3 to 4 times. And the first one's going to be rough. It could be accurate, it might not be. Regardless, you take your first value and you put it into the rough titer. So for our experiment, we got 26.30 centimeters cubed. Okay. Now, next we have to generate a table of results, okay? So we have 7 marks here. The first mark, right here, is for 1 having 2 burette readings. Okay, I'm just going to use a different color. 2 burette readings. 1, 2. Or should I just combine the 2 here? Okay, 2 burette readings. The second that's the first condition. The second condition is you have to have 2 or more accurate titrations, and we have 3. So 2 or more accurate titrations. What are accurate titrations? They are titrations that are within 0.1 centimeters cubed of each other. That's for our first mark. Now for our second mark, we have to have titer values recorded for accurate titration, so these titer values, these ones right here. And then we also have to have correct headings and correct units. We also must have an initial, a final, burette reading, a titer, volume, and have used centimeters cubed to get our second mark. Now for our third mark, all accurate burette readings must be to the nearest 0.05 centimeters cubed, meaning they either end in a 0 or they end in something point something 5. That is because we have to take our answers, or our answers have to be to the precision of the instrument we're using. And in this case, the burette can record up to 2 decimal places to the nearest 0.05 centimeters cubed. Our 4th mark is for a final accurate titer to be within 0.1 centimeters cubed of the other. Again, reinforcing the idea of accuracy. Right? Now, these marks, 5, 6, and 7, are comparing your results to the supervisor's results. So a supervisor would carry out the experiment and compare his results to yours. The closer your answers are to each other, the higher the marks you gain. There is a range, so there is room for error. You don't have to have the exact same answers, but you have to have answers within close proximity to gain full marks. Okay. Now let's answer these series of questions. From your accurate titration results, calculate a suitable mean value to use in your calculations. Show clearly how you obtain your mean value. Okay, so since I have 3 identical titers, I'm just going to place ticks next to each one just to show them that these are the results that are most accurate. Now, there's no need to calculate a mean. I'm just going to put down 225.95. But if we had different accurate readings within 0.1 centimeters cubed of each other, but they were different values, you would add them all up and divide them by the number of values. So let's say we have 26.01 plus 26.02 plus 26.03. You'd add them and then divide them by 3. And you have to make sure that the spread is no more than 0.2 centimeters cubed for sure. And that working out must be shown. So either working out or ticks, and that the decimal, the answer is rounded to 2 decimal places to gain the full mark. Okay? So moving on, it then says to calculate the moles of citric acid in 25 centimeters cubed of FB1, which had 7.5 grams per decimeters cubed solution. Okay? So if per 1 decimeters, because obviously it's per 1 decimeter cubed, we have 7.5 grams, and here they're asking for how much is in 25 centimeters cubed. What we need to do is convert centimeters cubed to decimeters cubed by dividing by 1,000. So this 25 centimeters cubed is equivalent to 0.025 decimeters cubed. We divided by 1,000. So if we cross multiply, we find that there is going to be 7.5 times 0.025 grams in 25 centimeters cubed. So there's going to be 0.1875 grams of citric acid. Now it's asked for the number of moles. The number of moles is equal to the mass divided the molar mass. So we have the mass, we have 0.1875 grams. The molar mass, if we add the individual atomic masses that make up citric acid, which has the following formula, we add them all up. So 6 times 12 plus 8 plus 7 times 16, we'll get 192. Divide our mass here by the MR here, and we end up with our molar mass, which is 99.77 times 10 to the power negative 4. This must be from 3 to 4, significant figures. And yeah, as alongside working out, you get your 2 marks. Then it says calculate the amount in moles of sodium hydroxide in the volume. So our sodium hydroxide had a concentration of 4.5 grams per decimeters cubed. And remember, sodium hydroxide was what we had in our burette. We had an average titer of 25.95 centimeters cubed, the equivalent of 0.02595 decimeters cubed. Again, we would multiply them together to eliminate, because really 4.5 grams per decimeter cubed is equivalent to 4.5 grams divided by decimeters cubed. Timesing by this decimeters cubed will cancel out the decimeters cubed, and we'll end up with just the grams. So, oh my bad, that would end up giving us 0.116775 grams. Now, they did say moles, so again, we're doing our mass divided by our MR. Sodium has an atomic mass of 23, oxygen 16, hydrogen 1. Add them all together, you have a molecular mass of 40. So our mass 0.116775 divided by 40 equals 2.92 times 10 to the negative 3. Again, from 3 to 4 significant figures. Okay. Then it says citric acid is triprotic. What did we say that meant earlier? That means each acid group, so COOH group, each hydrogen attached. So each acid group has one hydrogen. The more hydrogen groups or the more functional groups equivalently basically, the more hydrogens are donated or can be donated, my bad, sorry. So if citric acid is triprotic, that means it has 3 functional groups, 3 acid groups that donate protons, not 3 functional groups. It could have more, but 3 acid groups for sure. So what can we do? Well, we have the moles of sodium hydroxide. We have the moles of citric acid. What we need to do is, since we have ratios, we divide these ratios. It's important to know that when you're calculating 2 moles, usually what you're doing is you're going to have to divide them by each other eventually to, find the ratios between them for whatever reason. So in this case, when we divide the bigger number by the smaller number, we end up with 3. 3. Meaning, yes, it is triprotic. Tri meaning 3. So this result supports the statement. To gain the mark, you need to do this, and you need to mention that you support the statement. Having the working out alone is not enough, okay? Then it says complete the equation for the reaction of citric acid with sodium hydroxide. An acid and a base will always produce water, okay? Now, what is produced here is a salt. Since we have 1 mole of our citric acid, that means our salt, there must be C6 involved. And really, well, if we're trying to balance these out, what happens when we have an acid and a sodium hydroxide? So when an acid and a sodium hydroxide react, we remove water. But remember, this is a triprotic acid, so technically it has 3 carboxylic acid function groups. So that means 3 spaces would react with each functional group, right? So meaning we would actually lose 3 of our hydrogens to water. And we would lose 3 of our hydroxides to water from sodium. However, we still have the same number of oxygens, okay, because the oxygen is coming from the hydroxyl group, and then we will have 3 sodiums replacing. So just to look at it from here, you'll have COOH, and then NaOH. So really, these two. So this will be eliminated. Instead, the Na, the sodium, will bond to the oxygen, and these two form our water. And then this would happen in 3 different spaces because we have a triprotic acid with 3 COOH groups. It then says the citric acid does not contain a chiral carbon atom. Draw a possible structure, okay? So, no chiral carbon atom, so no single C central atom is bonded to 4 different groups. Or else, it wouldn't be a... Sorry, I've lost my train of thought. What I'm saying is, chiral carbon atom is bonded to 4 different groups. Otherwise, it's not a chiral carbon atom, okay? Now, we have to be very careful because although we know that there are 3 carboxylic acid groups, we can't say for sure that those are the only functional groups present. If we look at the formula, we have C6H8O7. COOH has 2 oxygens, and if we have 3, then there's 6 oxygens. That means there's an extra oxygen group. What this would mean is it's probably a hydroxyl group. And if we draw this out and it aligns with the formula, then we've got our correct molecule. So I'm just going to start with 2 carbon atoms. I'm going to draw my first functional group. And then I'm going to draw another carbon atom. And then another carbon atom. OH, and then another COOOH. Now if we take a look, now we have our 3 COOHs, and we added an extra oxygen hydroxyl. There's no way that's just singly bonded to an oxygen, because then it would have to have a double bond, and then it couldn't bond to this, could it now? And if we add them all up, we have 6 carbons. Yes, 1, 2, 3, 4, 5. Wait. Oops. It seems like I've missed out a carbon. My bad. That's why it's important to double check. 6 carbons, 8 hydrogens. Let's check. 1, 2, 3, 4, 5, 6, 7, 8. Yes. And definitely 7 oxygens. So there you go. There is not a single carbon that is bonded to 4 different groups, okay? Now here it says a student used a pipette, 25 centimeters cubed, with a plus minus standard deviation of error of 0.06 centimeters cubed to measure our FB1, which is our citric acid. The student suggests that this is more accurate to measure the volume of the citric acid with a burette than it is with a pipette. So our pipette had an error of plus minus 0.06. Our burette can measure to the nearest 0.05 centimeters cubed. Since we read both a bottom value and a top value, there's an error at 2 points, whilst with a pipette, there's only an error at 1 point. We will have double this error, so 0.05 times 2, which equals 0.1 centimeters cubed. So a burette has 0.1 centimeter cubed plus 1 uncertainty, which obviously is greater than 0.06. 0.1 is larger than 0.06. This must mean that the student is not correct, because if our uncertainty of our burette is greater, then it is less accurate. Okay, so now we're going to determine the enthalpy change for a reaction involving aqueous citric acid with sodium hydroxide to form aqueous sodium citrate. FB4 and FB5 are both citric acid. FB4 is to be used for experiment 1, and then FB5 is to be used for experiment 2. And then FB6 is 2 moles per decimeters cubed of some sodium hydroxide. Now, in experiment 1, we're going to determine the enthalpy change of solution for citric acid. This is when 1 mole of citric acid dissolves in water. So the method is as follows. You're going to support one of the cups in a 250 centimeter beaker, okay? So this is our beaker, this is our cup. You're going to use 50 centimeter cube measuring cylinder to transfer 30 centimeters cubed of distilled water into here. Then you're going to measure the temperature of the water using a thermometer, I assume. And then you're going to record this temperature in the space for results. So I'm going to highlight record in blue. Then we're going to weigh the container with FB4, okay? So the container containing FB4, our citric acid, we're going to weigh it. And then we're going to tip all of this into the cup. Then we're going to stir the mixture until a minimum temperature is obtained. So we're just going to swirl it gently. And then we're going to record this temperature. Then we're going to, again, re-weigh, but this time we're actually re-weighing the residue This is any bit of citric acid that was left behind. Even if it is small droplets, we want to make sure we know exactly how much we have transferred, and then we're going to record that mass. Okay, then we're going to calculate and record the mass of FB4 used. So that is how much we added, being how much was present first and then how much remained. And then calculate and record the temperature change. So our two temperatures recorded here, and we're going to calculate the difference. Okay, so as you can see, I've generated a table. I have added 6 columns. This is for every time it said record or calculate. As well, there's a record here as well, my bad. Now, our 3 marks are based off of a set of rules. For mark 1, we needed to have the correct headings. So mass of container, container plus residue mass, and the amount of FB4 added, given the correct units, grams. For the second mark, we had to have the initial temperature, the final temperature, and the temperature change all in degrees Celsius. Okay? Technically, change in temperature doesn't really need a unit because change has no unit. And then for our third mark, we have to have both balanced readings given to the same number of decimal places. So the same way I use 2 decimal places here, I use 2 decimal places here, I will use 2 decimal places here as well. And thermometer readings must end in either 0.0 or 0.5 degrees Celsius, like so, as this is as accurate as a thermometer can get. Then it says to calculate the energy change. Okay, so energy change represented by Q is equal to MC delta T. M is the mass of the thing being heated, so our water, our 30. Okay, C is our fixed specific heat capacity, 4.18, and T is our temperature change, was 2.5. Multiply these 3 together, and what you get is 313.5 joules. Okay, then it says to calculate the enthalpy change denoted by delta H1 in kilojoules per mole. Notice the change in the units. This is we often use joules with energy change and then kilojoules per mole with enthalpy change. For dissolving 1 mole of solid citric acid in water, show you're working out. So the formula for enthalpy change is delta Q over N, energy change over moles. We have to convert that that energy change into kilojoules first for the units to be correct. So what we're going to do is, we know that our joules is 313.5. Our moles is our mass divided our MR. So to calculate the denominator, the moles, we do our mass, which is our 3.4, divide 192 to get whatever, and then our 313 divided 5.5 divided by 1,000 to turn it into kilojoules, okay? So this is our moles, 1.77 times 10 to the negative 2. Then our delta H is our joules divided by 1,000 divided by our moles, ends up with 17.7 kilojoules per mole. Is this a positive or negative value? Well, it is positive because, as you can see, the final temperature of the water is decreased. That means temperature was taken from the surroundings inwards, so it's endothermic reaction. So it must have a positive enthalpy change. Okay, now in experiment 2, we're going to determine the enthalpy change using 1 mole of solid citric acid with aqueous sodium hydroxide. The sodium hydroxide, our FB6, is going to be in excess, and our solid citric acid is our FB5. The method is as follows. We're going to support the second cup in the beaker, and then we're going to add 4.8 to 5 grams of FB5 to the cup and record our weighings. Now, how we're going to do this is we are going to add the 4.8 to 5 grams of our solid citric acid to the container and then weigh it before, transfer it, weigh it after to see how much has been transferred, but it should be around 4.8 to 5 grams. So it would be best to transfer 5 grams so that any transfer will ensure that it goes no lower than 4.8 grams. It says measure and record the temperature of FB6 in the container. So FB6 is our sodium hydroxide. Sorry, this is our FB5. So we've transferred the FB5 to the cup and we want to measure its initial temperature. And then we're going to add 50 centimeters cubed of FB6, our sodium hydroxide, which is excess, by the way. And we're then going to stir. Then we're going to measure the maximum temperature. And then we're going to record, and then we're going to calculate the mass of FB5 used and the temperature change once again. Okay, so I've generated a table of results. We have the same column headings as we did for the first experiment. The only thing is the amount of citric acid added needs to be 4.8 to 5 grams. And, yeah. Besides that, the third mark's really just accuracy, comparing your answers to the actual answers, and the second one as well. The first one, like I said, being the mass is correct, and there are correct subtractions here and here. And yeah, temperature changes are correct. Okay. So then it wants us to calculate the enthalpy change. Now it's worth 2 marks and we're going to really just redo all the steps we did with the first one. You find the energy change, Q equals mc delta T. We have 50 centimeters cubed of sodium hydroxide this time, 4.18 specific heat capacity always, and a temperature change of, according to my table, 3. This gives us 627 joules. Then we want to calculate the number of moles so we can calculate our enthalpy change. So mass divided MR. According to me, we had added 4.85 grams, divided by our MR, which we know to be previously 192. Sorry, I'm revealed the wrong one. And then we get this number of moles. So then for the enthalpy change, we need the energy change over the moles. But remember, we need to go from joules to kilojoules. So we have to divide by 1,000 to end up from 627 to 0.627 divided by our number of moles to give us 24.8. Is this positive or negative? Well, take a look. Has the temperature risen or has the temperature fallen? It's risen. That means there's heat energy released to surroundings, so it must be an exothermic reaction and have a negative sign. Now here it says to use the 2 enthalpy change values to find the value for the enthalpy change between citric acid, sodium hydroxide. Acid plus base is equivalent to a neutralization reaction, which is going to be exothermic. Neutralization reactions are exothermic. We should end up with a negative value. The only way we can end up with a negative value is if we subtract H1 minus from H2, otherwise we'd get a positive value. So that's your easy way of going about doing this, and then you'd get negative 42.5 kilojoules per mole. Now onto the qualitative analysis bit. We need to make sure that any observations made should include color changes, precipitate formations, solubilities when applicable, formation of any gases, and tests that identify these gases. Every stage should be recorded, every observation at each stage should be recorded. No changes observed must be noted as no change. Correct names, formulas should be used. If a solution is warmed, then boiling tube. If a solid is heated, then a hard glass test tube must be used. Must rinse in between where possible so that we can reuse test tubes and boiling tubes when possible. No additional tests should be attempted, only those on the paper. Okay, so now we have to deduce the formula of FB8. These 3 stand out to me the most. So if we look at the first one, potassium iodide solution turns brown, this could be an indicator that iodine is formed. Now, this could mean a couple of things. It could be that halide ions like chloride ions or bromide ions are displacing it, or it could mean something else. However, test 3 makes it very clear that there are actually halides present because a white precipitate forms, and this indicates the presence of chloride ions. So this is our anion. And then in test 4, we have a test with aqueous ammonia, and we have an observation of a brown precipitate being insoluble in excess. Remember, with precipitates, always state what happens when in excess. And if we go to the back, we can see that in our table, this same observation can be made with Fe3 plus ions. With ammonia, they form a red-brown precipitate that is insoluble in excess. This means that there are Fe3 plus cations present. Now, there are 3 plus charge on Fe3 plus ions and a negative 1 charge on chloride ions. So for every Fe3 plus ion, we need 3 chloride ions. So the formula must be FeCl3. Then it says to state the number of all the tests that involve a redox reaction. So I've just written out the equations for each one. As you can see in test 1, the reason why we had the iodine form is because Fe3 plus ions actually oxidized the iodide ions into iodine. Them themselves were reduced. And in the second equation, same thing. They oxidized the zinc to form zinc ions. However, in tests 3 and 4, you can see that their aqueous ions, in both cases, go on to form solid forms, but the states aren't changing. It's still a plus 1, a minus 1 here. It's still a plus 3, a minus, and then 3 of them here. So nothing's really changing in terms of oxidation states. Nothing's being reduced and oxidized. And for a redox reaction to take place, you need both oxidation and reduction to take place at the same time. That's what's happening in tests 1 and 2. So it did say then to give the ionic equation for the reaction of one of the reactions in test 4. Now, I have put this one down, so you just need to use your symbols. And that is Fe3 plus ions react with the hydroxide ions to form iron hydroxide. There are a few other equations you could choose from, of course, stated in the mark scheme, but I just think this one would probably be the most easiest one. So yeah. Okay, so as you can see here, I've just written out the 2 other equations you could have used. This would be for Fb7. As you can see, the observation we made was the presence of a blue precipitate soluble in excess to form a deep blue solution. This indicates the presence of copper 2 plus ions, because that's the observation we get with copper 2 plus ions. And these are the 2 equations that you just have to have memorized that would take place here. And we had to obviously state our symbols as well, because that matters. For the second equation, copper 2 plus ions could have been solid as well. It doesn't matter. But everything else should be identical, basically. Now it wants us to carry out tests to identify Fb7. And it says that the anion present in Fb7 does not contain sulfur. We must record the tests and observations made for this identification process, basically. You must use a boiling tube if any liquid is heated. So we've already established that the cation is copper 2 plus ions based off of this test right here. Now we just need to find the anion, and they said it doesn't contain sulfur, so you can already cross off these from our anions table. And then if we look back here, we said that there was no change with silver nitrate. This means there are no halides, so we can also cross off these 3. Therefore, we have to distinguish between whether it's going to be a carbonate ion, a nitrate, or a nitrite. So, carbonates ions are different from nitrates and nitrites, and that is, with an acid, they will give off a gas. Okay? So, the first thing that I'm going to do is I'm going to try and eliminate carbonate ions. So, I'm going to do this by adding a dilute acid, and then I find that there is no change according to the mark scheme, okay? Which means we definitely do not have carbonate ions, because CO2 would have been produced with an acid. So now we're stuck between these 2, okay? So what I'm going to do is, if we look at our table, they both have reactions with ammonia upon heating with sodium hydroxide. Sorry, they both produce ammonia when you heat them with sodium hydroxide and aluminum foil. However, there's an additional step with nitrite ions that we can use to see whether or not this occurs, okay? So we're going to add excess NaOH to FB7, and this is important, heat, and this is important as well, add aluminum or aluminium. Otherwise, we won't get the marks for this step. Okay, and then we get a gas, of course. This gas we should test. So with litmus paper, it's going to turn blue. Oh wait, sorry. Turns blue. Because this is what we expect, because obviously ammonia is present. So it's going to be the same for both. Then what I'm going to do is I'm going to add acidified KMNO4 according to the table, and then apparently according to the mark scheme we find that it's not decolorized, which means it's not nitrite ions, it's nitrate ions. So we have nitrate ions. Therefore the formula, well, if you take a look, copper ions have a +2 and nitrate ions have a -1. So for every copper ion there are 2 nitrates, so the formula is copper NO3 in brackets 2, so we don't mix up the 3 and the 2. And then there you go, that's it.